Okay, so chapter 6, we've been dealing with basically things that look linear. Linear was kind of our whole point. Um, and so we've done a few different things. We've looked at linear equations and solving them, especially if they're only in one variable. What we're going to do today, eventually, is we're going to get down to doing two variable linear equations, two variable. So that will be interesting. That'll just bring a completely different set of information into view on that. The last thing we're going to do in chapter 6, we're going to talk about linear inequalities. So far we've been doing linear equations, and as we've mentioned before, the word equation implies that there's an equal sign. So you got an equal sign, you got this thing equal to that thing. And there's all kinds of things we can talk about with that. But an inequality inherently uses a less than sign, a less than or equal to sign, a greater than sign, a greater than or equal to sign, or very rarely the not equal to sign. So that will kind of be what we're going over here. So a linear inequality, it's going to look something like that. It may not look exactly like that. So what you have to realize is that it's linear, not because it looks exactly like it's written in that form, but because the only possible things you got going on are instances of your variable x, and it's not x squared, x to the third, square root of x, anything funky, it's just x. And then you just have numbers flowing around out there. Oh, you might have a coefficient, you might have some constants flowing around. That's what makes it linear. And there's all kinds of funky ways it can be presented to you. For example, yes, it might be great if it was written just ever so delicately, like these. That fits this form here. B is -7, A is 3, C is 5. But in practice, you might not actually get that. 4 greater than -2x. 13 minus 2x less than 5x. You might get all kinds of funky business when you're dealing with all of this. It may not work out exactly the way you want. It may not look pretty, but that's okay. It's linear because it's just a single x. It's not trying to do something fancy. You bring x squared into the business, that literally is what makes it no longer linear. So linear has a very specific kind of definition. So this we know will not be linear. Now we can still talk about that, but that would involve us understanding a thing or two about quadratics, which we're not going to talk about. We'll keep them off the table. Yeah, the less the merrier, right? Normally, the less you have to learn, the easier it is, right? You know what life's all about? It's about taking the easiest path. I'm kidding, it's not. It's about challenging yourself, and well, really, it's about making a lot of money, but that's not true. But for some of us, it's true. Some of us are like, well, yeah, you just make as much money as you can. So just like solving an equation is the process of finding whatever values for the variable will work and make the equation a true statement, it's exactly the same for solving an inequality. You're trying to find all possible values of x, and there could be an infinite amount of them, but you're trying to find all possible values of x that would work, that could be plugged in all the way back in the original equation or inequality and create a true statement. That's all it is. So solving sounds harder than it is, but if you keep it in that context, I think you'll benefit. In fact, what we're going to see is with linear inequalities, in almost every case, you're going to have an infinite number of possible solutions. And we're just going to have to remember that. So that's what the solution set is. It's the set of all possible values. So there's a couple ways that you can write this. And you know what? Let's zoomify. You guys can all hear me out there in the zoomosphere. Is that correct? Everyone can hear me? Yes, thank you very much. Very good. Okay. Not you guys, that little box that came up. I wanted it to go. Very good. Thank you. I'm glad you are able to hear me. Appreciate that. So let's look at some of the possible ways a solution set can look. Well, this is saying all x, you know what, I'll just type it out. This is literally saying all x, all values of the variable x, such that, so that vertical bar here is just saying such that, or it's giving the conditions. X is less than 3. All real numbers less than 3. So when you go to graph that on a number line, you're going to actually use shading. And how many of you want to hear a really lame joke? You guys want to hear a really lame joke? We in the mood for a lame joke? Yes, we got a sure. Oh boy, I don't know if you guys are ready for this, because if you know anything about my jokes, they are very bad. All right. I apologize in advance. But whenever you're shading, you'll make the number line, you'll use a pencil or pen if you were writing it on paper. You would want to make sure that you use really thick shading as opposed to really slim shading. You don't want slim shading. Any other form of shading would merely be imitating. So want the real slim shading, please. Please, that's all I can do. Okay, I apologize for that joke. So, is Mr. Gunther funny? The jury's still out on that. Anyways, so this is saying all x values less than 3. No, that was great. Hey, I appreciate that. I appreciate that. And it's not like you're incentivized to just lie to me and say nice things to me. It's not like, anyways. So what we're going to see is it's all x values less than 3. So we take the number line, we shade everything. And notice the shading has an arrowhead because we're shading all the way down to negative infinity. And then we stop at 3. Now, since we can't include 3, since it's strictly less than 3, so 2.9999999 is included, but the number 3 itself is not included. What we do on the number line, well, we still have to think the number 3 is still important even if we can't attain it. So that's why you see that open circle there. That open circle means everything, but except you can't have the 3 itself. So that's what that open circle is going to mean. Yeah, that's about all I have to say about that, Pilgrim. This next set is all x such that x is greater than, or it can also be equal to -1. And let's see if I can't move that so it's a little easier to see that. That's what this next set is saying. So as you see now, -1 is kind of the anchor, it's the important value. We shade everything to the right of it because we want everything greater than or equal to 1. And now we can include the 1 because it's or equal to. So -1 is allowed. And so now we don't use an open circle, we use a closed circle saying that the -1 is itself an allowable value. And it's just about that simple. Finally, this last one is saying all x, or all x values, such that x is greater than -1, but less than or equal to, give myself one more space, less than or equal to +3. So this is like they're sandwiched in there. They're sandwiched a little bit. It's all x values between it. So 0 is allowed because 0 is strictly greater than -1, but less than or equal to 3. 1 is in there, 2 is in there, 3 is also in there, that's the very end of it, but it is in there because there's a closed circle, and it's because we can be or equal to 3. -1, though, is not in there. There's an open circle on it, and it's because we have to be strictly above -1. But everything just a hair above -1 is included. That means it's not just whole numbers, because whole numbers are just the nicest thing to write on a number line. But you can also say negative 0.5, negative 1/2, which would be right around here, is in there because it's in the shaded region. 1.5 is in there. Pi minus 1, so 2.14159 is somewhere in here. So there's all kinds of things that are in there. In fact, this what we could say, there's an infinite amount of numbers that are between negative 1 and 3. There's an infinite amount. You could do, okay, just to demonstrate, you could do 1.2, 1.22, 1.222. You could go out to as many decimal places as you want, and there's no limit to the number of decimals you could go out to. So the way I like to think about this open circle, closed circle business, you might also, first of all, a quick note, you might also see that as you use a parentheses on an open circle and a bracket on a closed circle, a nice hard bracket with nice, I'll draw it even better, nice, well-defined 90-degree angles. So here you'd use a parenthesis, here you use a hard bracket. That's just another notation for it. It's the same idea. Because the bracket looks more definitive, it looks like you can actually be on it. The parentheses is your California cousin who just lives on the beach. That's nice. I wish I could do that, but I don't like California all that much because I like breathing fresh air that is not polluted. Anyways, the way I like to think about it, open circle, you can go up to the 3 here, but you can't quite be on the 3. I like to think about it as a regular fence versus an electric fence. An electric fence still tells you the boundary, but you don't want to touch the electric fence itself. You can get just right up to it, but you don't touch that thing, or you're going to get a shock. So the open circle, the parentheses idea is like an open fence. Excuse me, an electric fence. This, though, is just like a regular metal fence, not electrified. You can touch it. You can't go past it, let's say, but you can go up to it and touch it. So electric fence versus regular fence is just kind of a different way to think about it. What we're going to see is that for most of the inequalities we solve, the solution sets are going to look something like this. In fact, here's a list of all the possibilities. These are all the ways you can express things, graphing subsets of a real number. Don't get confused too much by the vernacular there, by the words. Words are evil. We call this type of notation, we call it set builder notation. You use these set brackets here and here. You use this X and this vertical line. We just call it set builder. So you're saying all X such that X is less than some number A. It'll look like this. Open circle, because it's got to be strictly less than it, shade to the left. Here, this is X less than or equal to A, so we use a nice closed filled in circle, shade everything to the left. And so on and so forth. You can do all things greater than a certain value. You can do things in between, and you can have open circles on both. That would look like this. It'd have strict less than signs. You can have closed circles on both, and then so the inequality symbol would have to be the or equal to 1. Then you can have what are sometimes called mixed form. One of them has a closed circle, one has an open, and you just come over here and you look, okay, the A had the closed circle because there was an or equal to inequality sign. The B had the open circle because it's a strict less than. And then you can flip them, flop them. So there's really only so many forms that a solution can take, that the solution set can take at the end of the day. So solving these, though, that's a different question. Solving them is a completely different beast. There we go. Basically, the way you solve a linear inequality, you can almost just pretend like you were solving an equation with the equal sign and everything. You can almost pretend like that. There's only one important exception. If you are multiplying or dividing both sides of an inequality by a negative number, you need to reverse the direction of the inequality symbol. So, for example, if you started with a greater than, if you started with a greater than symbol, Then multiply both sides by, oh, I don't know, -3, any negative number. You got to flip the symbol. You just make it a less than symbol now. Or heck, if you started with a less than or equal to symbol, whatever, I'll just freehand it. Started with a less than or equal to symbol, and then for whatever reason, to solve it, you need to divide both sides by -1.4. I don't know why you do that, but if you had to divide both sides by negative, you flip the sign like that. You just have it face the opposite direction. If it started with an or equal to, it'll still have an or equal to. If it didn't have an or equal to, it'll still not have one. So that doesn't change. Okay, so let's ignore all this business. Let's solve this one ourselves. 6x minus 12 greater than 8x plus 2. So 6x minus 12, need a little more space than that. 6x minus 12 greater than 8x minus 2. Our goal is to solve it. So what we're looking for is all possible values of x that we could substitute in here and create a true statement so that whatever the left-hand side shakes out to is strictly greater than whatever the right-hand side shakes out to. That's all solving something really is at the end of the day. Well, we would just use our same solving techniques. If it was an equation, then just remember our one exception if it even comes up. It may not come up. So here, I want all my x's not to be in Texas, but to be on the left-hand side of the inequality. Yeah, exactly. Just like if it was an equation. I want all my x's on the left, usually. So I'm going to subtract 8x. I'll leave the 12 and the 2 alone for the moment. So 6x minus 8x, what is that going to give me? -2x. Very good. All right, what would I naturally want to do next here? Exactly. Now I want the x to be all by itself on the left. It's forever alone. I want to add the 12 to get rid of it, to get it over there on the right-hand side. So I'm just going to have -2x left on the left-hand side. Still a greater than, because I haven't done anything yet that would make me switch the sign. Not yet. And even though I've subtracted 8x up here, that doesn't flip the sign because I'm subtracting. If I were to multiply or divide both sides by a negative number, then I'd flip the sign. So -2 plus 12 is really the same as 12 minus 2, which is what? 10? Yep. Now what is the last stroke? Exactly, you're exactly right. You would divide both sides by -2 to get x by itself. But as Madeline pointed out, since you're dividing by a negative number, flip that sign. You think more exclamation marks will get the point across? Yeah, I think it will. Let's see how many we can go. Oh, one too much. Yes, you're dividing by a negative number, so you got to flip that sign. So, dun, 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 dun. What was once a greater than sign is now a less than sign. You're going to have x all by itself. And then 10 divided by -2 will give you what? -5. So you still get a negative number at the end of it. You just have to know to flip the sign. And I think the problem from the PowerPoint was 8x plus 2. So we're getting a slightly different answer because I just wrote it down wrong. Doesn't matter. This is the same exact thing. Same exact deal. So if you wanted to write that in set builder notation, you'd say all x such that x is less than -5. Well, that's just awful groovy, isn't it? Yeah, so the difference between an inequality and an equation, sometimes you got to flip the sign on the inequality. You're going to solve it almost completely like you were just solving an equation. And then you just have to know what the solution set looks like on a number line. Where do you shade? And do you want to use real thick shading or real slim shading? Always thick shading so it's clear what you're doing, because any other form would merely be imitating. So let's go ahead and graph the solution set. So this right here is our solution set. Let's graph it on a number line. Go away. Give myself a lot of space. Yada, yada, yada. And ooh, if I was, you know, if this was a normal semester and I was just in class writing on a whiteboard, I couldn't get nice straight lines like this. My drawing skills are somewhere between really, really awful and amazing, but they're more towards really, really awful. That means they're still in between awful and amazing. Anywho, so we'll put 0 over here. It doesn't matter where we put it. We'll put -5 maybe down here. And now I'll shade with a different color. Oh, what's a color you want me to shade with? Purple, the royal color. On purple shading, I would use a nice big open circle because I had strictly less than -5. You put that down there, the or equal to, get out of here. You got to fill that circle in. That's not the case. And now I can just shade everything. So even though the circle is really big, it's only meant to be right there just at -5 alone. But I can't draw a whole lot smaller than that and emphasize my point. And then the shading also follows down with this arrow. It goes down forever and ever down to -infinity. Does that make sense? You cool with it? Out there in Zoomosphere, in the Zoom world, does that make sense to use, guys? Use, guys, very good. Yay. Good, good, good. And if it doesn't, please feel free to stop me and say, what are you talking about, Willis? Where I will take the form of Willis. I need to stop making references to old sitcoms from the 70s. Or make more, actually. Let's solve another inequality. How many of you want to make it a little more interesting than that? Because that just kind of looks boring, right? Anyone? Let's make it interesting. It's always good. Now, if you're like, no, why would you make it harder? Well, we're in class and you're having a math person, a math expert, do it with you. So you'd rather it be harder while we're in class than while you're on the homework. So yeah, let's make it a little more interesting than that. Because that's just boring, in my opinion. So I'll make up a three-way inequality. Let's see, how's about, let's solve the inequality -17 less than or equal to 5x minus 4 strictly less than 12. And you know what? We're not done with this. We're going to make it even more interesting. We're going to make that -5x. And you'll see why that gets really interesting. That is a great question. So wait a minute. This is called a three-way inequality because there's 3 different pieces here. and there's two total inequality signs. Yeah, how the heck do you start this one? Well, very rarely in math does it do you just do the way you kind of would naturally think to do it. Usually math is like, well, hold on there, Pilgrim, you got to slow down. Here you don't. What we're going to do is you're saying, well, I got to get x by itself, so I'm going to add 4 to it, right? And it turns out I can add it to all 3 parts. I can solve this like this was one mega inequality. But here's really why. This, and I'll show you, this 3-way, not 2-way. Do you know 2-way? This 3-way inequality is really just these 2 inequalities sandwiched together. And I'll show you what those 2 are. This 3-way inequality is really just this. It's negative 17 less than or equal to negative 5x minus 4. And then it's sandwiched together with this other inequality, negative 5x minus 4 less than 12. So now let's start thinking about how we'd solve each of these individually. To solve this one, you'd add 4 to both sides to start, right? I would say, you know, completely ignore this one now completely. Pretend it's not even there. I would just add on this one 4 to both sides to get the ball rolling. So plus 4. But wait a minute. If once I take care of all that and solve this, I would have done the same thing over here because it's still negative 5x minus 4 is kind of the most important part. So on this one, I also would have added 4 to both sides. So wait just a darn minute. If I want to solve the full sandwiched inequality, I know I'd start by adding 4. So why not just do it to all 3 sides? And it would look an awful lot like I was doing it to each of these 2-sided ones. And that's exactly what's going on. So that's cool. The 3-way inequality, it kind of allows me to cheat. It kind of it's really not even cheating. It's still sound mathematical principles we're using, but it's a nice shorthand method. It's a nice way to save ourselves a little time and still do everything right. So that would leave me with just the negative 5x in the middle. I've added 4 to everything, so over here, 12 plus 4, 16, very good. I would still have this. Negative 17 plus 4, negative 13, correct. Very good. Hey, bada bing, bada boom, that's not so bad. It reminds me that it's not so bad. It's not so bad. Now, what would you naturally think to do next? Well, we want to isolate x, and we're going to actually just want to isolate it in the middle there. So actually, it's almost done, but we also need to get rid of what? Right, we're going to divide all 3 sides by negative 5. We're going to divide all 3 sides by negative 5. But wait a minute, we've divided by a negative number. Does that mean we need to flip signs? You bet. Yeah, you're going to have to flip that one. You're going to have to flip that one as well. So now we'll still write it from left to right. Let's see. Negative 13 divided by negative 5 doesn't simplify. And then the negatives, I'm doing a negative number divided by a negative number. So I can just call that positive. Oops. And just call that positive 13 over 5. It's the same thing. If you want, you could tell yourself the negatives cancel. I need to flip that sign. like that. Then it's just x by itself in the middle with Malcolm. Then I need to flip that other sign. 16 divided by negative 5, well, it's a positive divided by a negative. So the whole thing is just negative. But then 16 over 5 doesn't simplify because 16 is not divisible by 5. That looks ugly. My finger slipped. And now this is correct. This is an accurate way to write it, but it's not very pretty because that's not the order we like to write it in. That's saying 13 over 5 is less than or equal to x, which is greater than negative 16 over 5. Another way to write it is to say that x is greater than negative 16 over 5, but also less than or equal to 13 over 5. In any way, in other words, I can do like a mirror reflection and still be correct. So the mirror it. And you're still right. This is not wrong down here. It's not incorrect, but it doesn't, we're not reading it from left to right like we normally want to. Here, it's the exact same sentiment, but now read from left to right. We had to mirror it because we had to flip all the signs. Now, let's write the solution set in set builder notation. This is our solution in Spirit. Let's write it in set builder. Of course, we don't cover interval notation, which is actually the ultimately preferred way of writing it, but that's okay. So this solution set is all x such that, and you can just write exact, I mean, you can almost just reproduce it. Make this one bigger if I want. So this is saying all x such that basically x is between negative 16 over 5 and positive 13 over 5. And then you can't actually be negative 16 over 5 itself. You can be 13 over 5. Let's graph this on a single number line. Let's say 0 is in the middle here. Let's say 13 over 5. O is somewhere over here, and I'll label it in just a moment. Let's say negative 16 over 5 is somewhere over there. 13 over 5, which is 2.6. Here's 0 in the middle, negative 16 over 5, which is negative 3.2. And now we want to shade everything in between, but we're going to have an open circle on the, let me draw that a little bit better. Use an actual circle tool. We're going to have an open circle on the negative 16 over 5. We're going to have a closed circle on the positive 13 over 5. And then we are going to shade everything in between. Ain't that something? Would everyone say that's something? That is something. Everything is something. So it's, arbitrarily true, but yes, it is something. You guys in the Zoomosphere, did that make sense? That process that we did? Of course, you're always very good. I appreciate that. Yes, yes. CC Sabathia was a pitcher in the MLB for the Yankees, the Indians. Won a Cy Young. Anyways, Of course, we are recording this. Of course, you can go onto the YouTube channel, watch this video later, watch it at your own leisure, rewatch parts of it, whatever works for you. So that's gonna call it quits for chapter 6. That's gonna do it for chapter 6. Now let me just pull up our chapter 7 material. In the meantime, I want someone to give me a joke. Give me a joke. Someone tell me a joke. While I'm pulling this up, you can type it out in the Zumo box. You know, obviously it's got to be relatively G-rated. U.S. government. All right, Xavier, go ahead. What is your U.S. government joke? Oh, do you mean the subject itself? That the subject of U.S. government, that's the joke. The U.S. government is a joke, okay. Well, most people think all forms of government are a joke. Others think anarchy, lack of government is a joke. So that is one joke. Unfortunately, I wish I could say it's a funny joke. It's not that it's not a funny joke. It's that it's very sad, you know, if you have dysfunction in a government and you think it's not working, you think it's a joke, then yeah, you don't want it to be like that. Let's see here. Someone else give me a joke as I pull up our next round. Give me a joke. Give me maybe something with a punchline. The classic form of humor. But you only have about 2 seconds. Just need a few more seconds because I have now reached the threshold. We're at the next place. Here's just a quick little hint. You, the guys, the students, you have a lot of stuff due this. You have a couple of things due tonight, the 17th. But on the 24th, next Thursday, you have what looks like a lot of assignments due, if you've checked MyLabs Plus recently. I would not put it off until Thursday. No, sirree, Bob, you're not going to have that time. I would get the bulk of it done this weekend, and then on Tuesday during our review session, I would come at me hot with every question, every problem, issue you had with the MyLabs homework, and we can work them together because there's a lot. So do not save this homework due next Thursday, the 24th. Do not save it for that last day, especially because you're going to have an exam that day. So don't do that. Anywho, let's get back to it. Ta-da. Linear functions and their graphs. So we've dealt with, they're not truly functions, but we have dealt with linear equations in one variable. We just had x. Sorry about that. And oops, I think that's what the kids say these days. Linear functions and their graphs. So we've dealt with them in one variable, where it was just x was the variable and we had to move things around. Now we're going to look at 2 variables. We're going to have both a y and an x. We're going to have both a y and an x. And we come in here and we hit it hard and we just go right at it. No two ways about it. So an equation of the form a times x plus b times y equals c, where capitals A, B, and C are all real numbers. So let me actually write that. A, B, and C are all real numbers. So A, B, and C are real numbers. X and Y, though, are the variables. So they'll actually stay written as X and Y, for the most part, especially when we're talking about graphing them. A, B, and C, though, when we're actually out there in the wild, we're going to see that A, B, and C are actual just numbers. So they make straight lines. So we might need to have a little bit of a talk real quick because we're about to start graphing. We need to maybe have a little review, little talk about graphing. What does it mean to graph things? We technically did some graphing just a second ago in the last section when we were putting things on a single number line and shading the right areas. You were actually graphing, but you were only graphing in one variable. So now let us graph in two variables. Not ready? Well, I bet you're more ready than you think because we're going to do a real rudimetric, we're going to do a real ground up approach to graphing. So earlier, you were graphing things on a single number line. You had maybe some arrowheads at the end, and the arrowheads aren't actually part of the graph. They're just telling you that it goes on forever in that direction. Same over here. Now, before, when we were graphing like this, it was already implied that our only variable was x. So technically, we could have written x down there to say, hey, this is for the variable x. You could have done that. It wasn't required because it was just so obvious, it was implied. So in one variable, you just have a single number line like this. Well, if you're graphing in two variables, you'd need a separate number line for y, wouldn't you? Because now, instead of just having the variable x, we're going to have another variable, y, as well. So here's the other number line for y. That's great. And then we could come down here and we could label this as the number line attached or associated with our y variable. But the problem is these aren't really together on the same graph. These are like two separate number lines. And in math, we're trying to get them together. We're trying to get them dating and be together. So one possible thing we can do, well, wait, we got two variables. We want to graph things that involve both variables. We want them all on the same graph. That's the whole point. Maybe we can just drop one of the number lines onto the other. What's the problem with that? You can't see anything, can you? You can't just slap one on top of the other. It's ridiculous. You're not going to see anything. So instead, what do you think I'm going to do here? I'm going to do something real tricky. In order to be able to see both of them at the same time on the same graph, I'm going to rotate the y number line 90 degrees. And slap it onto the other number line. Whoa. I almost did my mob guy voice. Oh. Yeah, that's what I'm going to do. I'm going to just slap them together. And I'm going to do that by rotating one of them 90 degrees. You just have to. And I'll put the arrowheads back on. Hey, doesn't that look like old school graphing we've done, that we've seen before, that we've been using before? It's called the XY coordinate plane. What's really interesting is it's also called the Cartesian coordinate system. Not because it'll Cartesia, but because it's named after an about 300 years ago, a French mathematician and philosopher named René Descartes. And René Descartes is actually really interesting because it turns out a lot of the old school mathematicians, the people who did a lot for math, were not just mathematicians. They were also philosophers. And they thought about the world, and math just happens to be a part of that. Math at its highest form is actually just philosophy. Math is not grinding a bunch of numbers and calculating a bunch of nonsense. That's not what math is at all. It's part of it, it's a small subset of it, but in a larger sense, math is actually philosophy, and that's where it gets interesting, but that's also where it gets absolutely critically difficult. Anyways, René Descartes is really interesting to me. René Descartes was actually a Christian philosopher as well, and he hypothesized a new way to think about the world. He said the classical way before that was that we could derive things purely from reason and purely from thinking about them. And that was Aristotle thousands of years before Descartes who postulated that. And while others had come along, Rene Descartes made the best argument that actually we should base what we do, our actions, on past events or on things that have already occurred. So I'm sorry, it's the other way around. Sorry, Aristotle believed that we could be, it's called a posteriori versus a priori. And Descartes argued we could derive things purely from reason without having to observe the natural world as much. So it's kind of interesting that this guy this coordinate system that we used all the time in math up till now, that it's named after him, and he actually did way more than just math. He did a lot more. He's a very famous philosopher. Anywho, we can just call it the XY coordinate plane, and it just makes sense that it has to look like this. Now, what you're going to have is you're going to have coordinates or points. These coordinates or points have to have an X component and a Y component. You might have also heard it called an ordered pair. Ordered because the X value needs to come first, then the Y value. You can graph points, and we're about to have our break. You can graph points by making little divots on the x-axis, on the y-axis. Ooh, I'm just failing today. Hold on. And so, for example, if you wanted to see the point -2, 5. -2 is the x coordinate. Over here, as you go to the right, you're becoming more positive, just like a normal number line. 0 in the middle, you're going right. But since it's -2, we'd go 2 units to the left. And then the y value is +5, so we'd go up 5 units. And so -2, 5 is this point here, roughly. And I'll even put that next to it. The point 4, 0 will, you would have 4 as your x coordinate, so you start from the very middle, called the origin, go 4 units to the right, and then since the y coordinate is 0, you go up or down no units, and so it's on the x-axis itself. And so that's how you can graph points. That's how points work. These are called the 4 quadrants. Here in this upper right quadrant, the first quadrant, all x and y values are positive. Over here, all x values are negative, but y values are still positive because you're over on the positive part of the y-axis, but the negative part of the x-axis. Down here, both x and y values are negative because you're on the negative side of the x-axis and now on the negative side of the y-axis in this quadrant. And then in this quadrant, x values are positive, y values are negative. So I think that's as good as time as any to take our break. We'll be back around 1:45-ish. And let me take, I'll take attendance when we come back. So we were discussing basically graphing things, and it got interesting. Now what we're going to do is we're going to graph linear equations now in 2 variables. And what we're going to see is that makes for lines. That makes a line. And the way it's going to work, there's a couple different methods we can use to graph, but we can use the intercept method as it's sometimes called. So let's see what's going on. Let's say you have the function or the equation 3x plus 2y equals 6. 3x plus 2y equals 6. Okay. Well, the x and y in the equation here are literally can be represented by coordinates or ordered pairs in or on the xy coordinate system, in the xy coordinate plane. So here's what we're going to do. We want to, where this equation crosses the x-axis, we'll call this the x-intercept. And where it crosses the y-axis, and we'll call that the y-intercept. Let's think logically about it. Let's make our xy coordinate plane. Remember the horizontal axis, the one that's on the horizon here, that's always going to be our x-axis. We're not going to try and switcheroo on it. And then our vertical up and down axis, that's always going to be our y-axis. So let's think about it. We want to know this kind of equation here is going to make a line. It's literally just going to make a line like this. It could look like that. It could be a positively sloped line, something like that. But it's going to cross the x-axis and the y-axis at one spot each, as long as it behaves a certain way, and we'll talk about it. So look, here this line crosses the x-axis here, and it crosses the y-axis here. But it could also do it like this, and it can cross the y-axis up here, x-axis up here. So there's lots of different things it can do. But the principle is that whenever it's crossing the x-axis, when it's like this, the x-intercept, its y-coordinate is 0. Right here at this point, right there, it's on the x-axis, but its y-coordinate is 0 because it's not up and down on the y-axis, it's right here. So it's on the x-axis, that means that it has a y value of 0. This could be the point like 5, 0. 5 for x, 0 for y. And then inversely, where it crosses the y-axis, we would call that the y-intercept. Now, its y value can be something other than 0, it can be anything, but its x-coordinate is 0. If you think about it, because while it's up here on the y-axis, it's not to the left or right along the horizontal x-axis here. It's right in the middle, which is where 0 is. It's like if you go down to where it is on the x-axis, it's right there at 0. So guess what? That's actually going to be our guiding principle. We want to find where this equation crosses the x-axis. So if you want to do that, plug a 0 in for y, not x, plug a 0 in for y and solve for x. And that's going to be where we find the x-intercept. Down here, if you want to see the y-intercept where it crosses the y-axis, you plug a 0 in for x and solve for y. That's going to be our system. And now, once we know where it crosses the x and y axis, it can't take any kind of weird curvy shape and go like, ooh, something like that. It can't do that because when they're written in this form, they are linear. They are strictly a line. And you can completely determine a line with just 2 points on it. They do have arrowheads. They do go on forever. But yeah, that's basically how it would work. So let's demonstrate that. Let's demonstrate that. So we're going to do two things. We're going to find the x-intercept. Then I'm going to make a nice little vertical bar here. And then we're going to find the y-intercept. Well, then we'll have 2 points. We go graph them on a standard graph, and bada bing, bada boom, you found the line, and you're done. And that's pretty cool. So let's see. To find the x-intercept, we let y equals 0. We let the other variable go to 0 and solve for x. Which literally means I'm going to plug a 0 in for y. I'm going to have 3x, that's the same. But I'm going to plug a 0 in for y, which means it goes away completely. 2 times 0 is 0. 3x plus 0 is just 3x. And you're going to end up with 3x equals 6. Now, how would I think to solve that for x? What would I do here? Yeah, divide both sides by 3, exactly. Now y is out of the picture, and you're just going to get x equals 6 divided by 3 is 2. But my friends, that means I would go onto the x-axis and look for 2, and that is right. But what that really says is that the x-intercept is a point on the graph. And every point has an x component or an x coordinate and a y coordinate. So the x component is going to be that 2 we just discovered, but the y component is going to be 0 by definition, and because we plugged the 0 in for y all the way at the Gordon get-go, at the beginning of it. So our x-intercept is the coordinate 2, 0. So if I ever ask you to say, what's the x-intercept? Don't just say 2. That is technically wrong. You got to say it's 2, 0. It's a coordinate. To find the y-intercept, what are we going to do here? Exactly. In other words, we're going to plug 0 in for x now. Now we're going to do the opposite. We're going to let x be equal to 0 and solve for y now. So, plugging it in, we'll use blue. Now we're going to put a 0 in for x. And then 2y just has to stay as it is. Now 3 times 0 is 0, and then adding 0 onto something does nothing. So in other words, the x just goes away. Divide both sides by 2 to get y by itself, and you get y equals 3. But y doesn't equal 3. Y does equal 3, but the y-intercept is not just 3. Not 3, 0, but 3 is the y-coordinate. Exactly, very good. So now the y-intercept is 0, 3. So let's remember that. Let me pull up a nice looking graph, something very usable. I had something earlier, but I didn't like it as much. Let's get it labeled. Okay, now you're starting to speak my language. And it looks like crap. I want to pull up a graph for you. So that we can actually graph this bad boy. There we go, that's a little bit better. Okay, so we have an x-intercept of 2, 0, and a y-intercept of 0, 3. So let me show you what I'm pulling up here. Here's a graph I want to use now. Can zoom in a little bit. Now we said that we had an x-intercept of 2, 0. So I'll rewrite that here. The x-intercept was 2, 0. I don't even need to label it as the x-intercept because it's clear that it is. The y-intercept was 0, 3. So I'm going to label that. So let's see, 2, 0 is this point right here. It's 2 on the x-axis, 0 on the y-axis. So I'll put that point down schmau. 0, 3 is the y-intercept, so it's up here. And now I'm going to draw the line that connects those two, that passes through both of them. And I'm going to adjust it ever so slightly. Something like that. There we go. And then I'm going to draw arrowheads. And bada bing, bada boom, we just graphed ourselves a line. That's a handsome line. Hello, handsome line. I almost did a voice for the line to respond to what I said, but I think that might have been a little bit too weird, a little too next level. Maybe next time we'll do that. What we'll see, we'll call this line, we'll say it has negative slope because as I go from left to right along the x-axis, the line looks like it's going downwards, like it's going downhill. And so that's what it means graphically for it to have a negative slope. Does that make sense, everyone out there? Zoomosphere in class, does that make sense? Is that clicking? Very good, very good. I'm thinking you have already seen linear functions like this before and graphing them and all that. And this is just one possible way to do it. But there's nothing that says you absolutely have to do it that way. Now let's talk in more general principles about lines. Let's talk about the slope of a line. The slope of a line, what the slope does is it tells you how much does this thing change in the vertical direction, the rise, for every unit change in the horizontal direction, sometimes called the run. That's interesting. So they give you a little formula that it says if you have 2 points, you can find the slope of the line that connects those 2 points. And it looks nastier than it is. It's just saying how much do the y values change divided by how much do the x values change between those 2 points. And you got to keep them consistent. You got to start with whatever you're calling the second point. You got to start with it and subtract the first point off from it. One thing to note is that your x values shouldn't be the same. But if you subtract one from the other, you don't get 0. If they are the same, you actually have a vertical line. But we'll talk about that in more detail. Got to drink a little bit of water. So we can talk about slope. Let's do a few examples of slope calculations because those are pretty darn interesting in my humble and always correct opinion. So slope, we use a lowercase m. Why? Actually, I don't know, but we use a lowercase m. You might have seen, the standard form of a line is written as y equals mx plus b. Yeah, we'll cover that in a little bit, but m would be the slope. That is weird. It is so weird. It is also so Raven. And what you do is you can calculate the slope as the change in y values between your 2 points, which we'll do some examples in a moment, divided by the change in x values. Where you have 2 points, x1, y1. That's just saying the x and y coordinates of your first point. Compare that to x2, x-men united, y2, which are just the x and y coordinates for your second point. So let's do an example so that you can see what the heck Josh is talking about. Let's use a color other than blue. Let's spice it up. Maybe a little bit of green. Now, I've been told, Josh, you better not use green there. And I say, I'm going to fight the man. I'm going to fight the law. And I'm going to win. So green it is. So find the slope. Look, you got to find ways to entertain yourself, right? I mean, there's nobody who says I can't use green, but I find ways to make light of things, make fun. So find the slope of the line connecting the points. How about -3, 17? I'll give myself a little space. And the point 4, -21. Let's make it -3. And we'll do a couple different cases because I think that there's some interesting things to be gleaned from that. So here's what I'm going to suggest. We have this little formulation. The first point you see, call it x1, y1. Because it's the first one, you see. It actually doesn't matter as long as I was consistent. So if I want to call this x1, y1 and this x2, y2, that's fine. If I wanted to call this the second point, whatever, but make sure it's x2, y2, and then this one would be x1, y1. Don't do mix and match like x1, y2, x2, y1. You can't mix and match. And if you like fantasy football, Joe Mixon might be a running back for you. So we'll call that x1, y1. We'll call this x2, y2. Right, so exactly, we have 2 points here. This first point is -3, 17. It has an x coordinate of -3 and a y coordinate of 17. And we use x1 simply to say this is the x coordinate of the first point. This is the y coordinate of the first point. Exactly. It's so that we keep it consistent when we do the calculation. Because in the slope calculation now, it's going to be y2 minus y1. So it's going to be -3 minus 17 on top. On bottom, it doesn't want us to try and screw things up and do -3 minus 4. No. We need to do 4 minus -3. It just wants it to keep it basically consistent. So here's y2 minus y1, and it's always subtraction. If you happen to be subtracting a negative number, you turn it into addition. So it's always subtraction in the formula. Don't let negative numbers confuse you. On top, we're going to get -3 minus 17. What will that give you? Not quite close. Not quite. If we're doing -3 and we're subtracting 17, yeah, it'll be -20. Yep. You're already starting with -3. You're subtracting, so it's only going to get more negative. And so it's kind of like doing 3 plus 17, but with a negative sign in. And then 4 minus -3 really just becomes 4 plus 3, which is what? 7. Very good. So we get -20 over 7. Let's interpret this with the rise over run interpretation. It's a negative slope. What this means is that for every 7 units, the bottom number, I go to the right, the line, it can either rise or fall. Since it's a negative number on top, it's going to be fall. The line falls 20 units. Rise over run. So sometimes rising can also be falling. It's the same thing, just whether you have a positive or negative number. But at the end of the day, what you're going to see is because you have a negative slope, negative 20 over 7 is negative, your line is going to look like something that's falling, that is going downhill. It's going to look like that. It may not cross these exact X and Y intercepts, but it might move all the way around over here. Its steepness might be a little bit different, but ultimately it's going to be falling. It's going to be going downhill. Does that make sense? Very good, very good. Let's try another one. Actually, we're going to try 3 more. This other one is going to be a bit mundane, but we're going to do it. And then we're going to look at the next 2, and we're going to look at some interesting cases. We're going to look at some interesting cases. Let's see. I'll make 2 points. So again, same directions. Let's find the slope of the line containing these 2 points. Let's say those points are 4, 12 and -5, comma, oh, what would be an interesting one? -5, -6 is our second point. Okay. Challenge accepted there, Pilgrim. Let's call this first point X1, Y1. And guess what? It doesn't hurt to just quickly label it. Label it real quick on your paper. X1, Y1. Let me write this a little bit more further up here. Yeah, label it real quick. This then will be X2, Y2. The more you label, the easier it is to read what you're doing and figure out what to do with it. So your slope calculation then is going to be M. Let's not use gold. It's not dark enough. Use orange. It's going to be Y2 minus Y1 over X2 minus X1. So it's -6 minus 12 divided by -5 minus 4. All right, let's see. -6, you're already starting off negative. You're only subtracting 12 units from it, so you're getting even more negative. So what will -6 minus 12 be? -18. Very good. That's on top. On bottom, what's -5 minus 4 going to be? -9. Perfect. And then you're going to have a negative divided by a negative, so your answer is going to be positive, and then it'll be +2, exactly. And you could write it as 2 over 1. You could write it as 2 over 1, so that when you do the rise over run interpretation, you're saying this thing, for every 1 unit you go to the right, Shmea, this bottom number, you rise or go up 2 units. Rise over run. Now, what if you were saying, you know what, Josh? I feel like messing with you today. I feel like really just blowing everything up. Okay, you want to mess with me? Well, you better not, because I will alert the proper authorities if I need to. So I'm just buying time. I want to mess things up, Josh, and I want to call this first point X2, Y2. And I want to call this other point x1, y1. Now you can't mix and match. You can't call this x2, y1. None of that business. But it turns out it doesn't matter. If I would have given you the points, if I would have just said -5, -6, if I wrote that first and then 4, 12 second, that's okay. You're going to get the exact same slope, and it's not wrong. It's not just a coincidence. You're going to get the exact same slope for a good reason. So let's see. Now it's going to be y2, which is 12, minus y1, which is -6. And remember, you're subtracting, but then you're subtracting the negative number. You're always subtracting. If it turns out this value here is negative, then you have to tell yourself, I'm subtracting a negative, which is okay. And then on bottom, what are you going to get? Well, exactly. Now you're going to get 4 minus -5. Exactly. And again, it's okay to subtract a negative number. Because subtracting a negative just becomes addition, so it's especially nice here. You're going to get positive 18 over positive 9. Earlier you got negative 18 over negative 9. That's fine, the negatives canceled out. Here they're just positive, so you get positive 2, which can be written as 2 over 1 per your fancy. And the slope is exactly the same, though, so the rise over run interpretation is exactly the same. So now we have a positive slope. And a real quick and dirty graph of a positive sloping line would be one that looks like it's going uphill as you go from left to right. So something like that. And you can move the line all about. It could have some different steepness, something like that. But at the end of the day, as you go from left to right, it's going uphill. That's what it means to be a positively sloped line. Because I really just love each and every one of you, and I want you all to do the best, let's look at a couple more examples, and let's make them more interesting. We saw an example of a negatively sloped line. We saw an example of a positively sloped line. Let's see an example of a line that has no slope. That's just like flat, like you're walking on flat land. What we're going to see is for that to happen, the 2 points on the line, your y values have to be the same. So again, find the slope between these 2 points. Let's say those points are 14, -5. And let's say the other point is 37, -5. Okay, we see repeated y values. That's okay. We'll just call this x1, y1. We'll call this x2, y2. We'll do our slope calculation. So it'd be y2, which is -5, minus y1, which is also -5. On bottom, x2 minus x1, 37 minus 14, okay. But what are you going to get on top? Not quite. This is where they're getting you. On top, -5 minus -5 becomes -5 plus 5. Well, which would be 0, exactly. On bottom, I guess you'll get 23, which is a bad Jim Carrey movie, but on top, you're going to get 0. On bottom, 23. Remember, it's okay to have 0 on top as long as you don't also have 0 on bottom. If 0 is on top and a number which is not 0 is on bottom, the whole thing just goes to 0. If you want, you could call it 0 over 1 if you were bored. And now the rise over run interpretation says For every 1 unit I go to the right, the line, well, it doesn't rise because the top is not positive. It doesn't fall because the top is not negative. The line doesn't change in the vertical direction. It doesn't go up or down. So guess what? That creates a flat line. A horizontal line, it's parallel to the x-axis. Now, horizontal lines, they can go anywhere up or down like this, but the whole point is they have 0 slope, which makes sense. If something doesn't have any slope, it's just like flat land. It's not sloped, it's not slanted at all. So 0 slope corresponds to a flat horizontal line. That is our key takeaway. Finally, let's look at one more example. So if you have repeated y values, that means you have a horizontal line. Let's look at it one more way. Let's look at what happens when you repeat x values. It turns out when we went all the way back to that definition of slope, we actually are not allowed to have repeat x values. Look here. It says where x2 minus x1 does not equal 0. In other words, where they're not the same, because if they are the same, then you subtract one from the other, you get 0. So we're actually not allowed to repeat x values, but we're going to relax that so that we can see why we're not allowed to do that. So once more, let's use pink. Let's calculate the slope of the line that passes through the points 0, 4, negative 12. And the other point will be 4, negative 15. So different y values, but the exact same x value. Okay, so we do our standard business. We call this x1, y1, x2, y2. Calculate the slope. It would be negative 15 minus negative 12 divided by 4 minus, 4. Wait a minute there. What are you going to get on bottom? 0. On top, you'll get negative 15 plus 12, which becomes negative 3, but I'm not as worried about the top anymore. On bottom, I'm going to get 0. And what's one of our big no-nos in math? You can't divide by 0. Exactly. Uh-oh, what's the old thing? Is it uh-oh, Chef Boyardee, or uh-oh, what's that canned pasta? Uh-oh, SpaghettiOs? Oh, so it rhymes. Yeah, uh-oh, SpaghettiOs, that's it. No, I'm playing around. Yes, uh-oh, SpaghettiOs. Yes, I still eat SpaghettiOs. I'm a grown man. Thank you, Xavier, very much. The SpaghettiOs are correct. I'm a grown man who eats SpaghettiOs. Why? Because I'm living my best life. Get off my back. So, uh-oh, we're dividing by 0. That means we're going to have undefined slope. And remember, when you divide by 0, you get something, we just call it undefined. So the slope isn't 0, because dividing by 0 does not produce 0. The slope is literally not defined. There's no definition for it. It's not anything. What it secretly will point to is that when you graph that line on the XY coordinate plane, instead of being a horizontal line, it's going to be a straight up and down vertical line. But we'll talk about why that's the case a little bit more next time. It'll be a vertical line. So you can have vertical lines, horizontal lines, positively sloping lines, negatively sloping lines, and that's the 4 possibilities. You'll notice for vertical lines, they may not ever cross the y-axis. It's not sloping over. So it's hard to talk about x and y intercepts with vertical lines or horizontal lines. But if you have a line with a positive slope or a negative slope, then you will always have both an x and y intercept. If you have a vertical line, you'll always have an x-intercept, and the only way you'll have a y-intercept is if it happens to be the same as the y-axis. If I shifted it all the way over here, then it hits the y-axis an infinite number of times, which is just silly, but you can. Okay, I think that's it for new material for the day, and I've got some good news. How many of you want to hear the good news? Are you ready to hear the good news? If you're out there. Oh, let's see. If the top is -3, would it still be on the right? What do you mean exactly? That's a great question. How do you decide, hey, once I know it's a vertical line, how do I decide where it goes? It's because they both have an x value of 4. So that means they would cross the x-axis at 4. And that's how I know how to anchor it. But Xavier, if the top is -3, would it still be on the right? What do you mean by that? Does that make sense, Xavier? Did that make sense? Yeah, but that's actually something we'll talk about next time. Yeah, the only way it would have to cross the x-axis at 4, this same as the points here, because that's the only way it's also going to come down here and cross at 4, -12, and 4, -15. But we'll actually talk about that next time. This was just kind of an introduction to the different types of slopes. Good question, good question. But let's talk about the good news. I didn't quite get through this entire section of 7.2, so I'm actually going to omit it from your exam. In fact, let me go do that right now, but we're still got some time left, so I want to work some homework problems. So while I go and change a few things real quick, just take me 2 minutes, get some homework problems you want to see done. We'll go till about 3, and yeah, I'll work some homework. You don't even have to bring up the entire homework problem and give me all the numbers. You can just say, can you work from my labs? Can you work this homework section number 12 or whatever? You can totally do that. Okay, so the first homework assignment we're going to want to do, the first homework problem is going to be a fractions problem. And let me just write it down real quick so I can transcribe it. I'm getting okay. So we're solving an equation that has some fractions involved in it, and the equation, now Xavier, I might be getting slightly different numbers than you. So I'll write the equation I see because it generates slightly different numbers per person. I'll write the equation on the board, but if you want, I can use your numbers if you want me to just edit it real quick. The equation I'm seeing is this. And let me turn on. And this is section 6.2 homework, number 21. And so Xavier, do I need to change up any of the numbers, or are you good with me just doing this one and it's similar enough? I'll let you decide, my friend, mi amigo. Okay, we'll change up the numbers very slightly. This is a very similar problem. Just to align with what you got, y over 9, 1/4, y over 4, minus 1 over 4. Very good. Okay. So we got this one. We see that there's fractions. Our usual kind of goal, our usual hope is to get rid of fractions, isn't it? Because we want to solve for the variable. Now, sometimes the very final answer might be a fraction, and that's unavoidable. But let's see what we can do. Let's see. We've got a couple denominators floating around. We've got 9s and we've got 4s. What we need to find is the least common denominator between 9 and 4. And really what that secretly is it's the least common multiple of 9 and 4. The least common multiple of 9 and 4. So maybe you can see in your head it's going to be 36. Maybe not, that's cool. What we're going to do is we're going to take and we're going to list out the multiples of some of these. 4, 18, 27, 36, 45, and I'll just put dot, dot, dot. This is an okay way to find the LCD. 4, 8, 12. Now we need to keep going until we see something in common with the multiples of 9. 4, 8, 12. I don't see anything yet. Uh-oh, what was it? Chef Boyardee? Ravioli. It was SpaghettiOs. Uh-oh, SpaghettiOs. I'm kidding. You should all learn right now that I am never serious, except when I'm grading your exams. And oh gosh, I keep listing out multiples of 4, and I don't see anything common with the 9 yet, but oh, thank goodness there's that 36. So the least common multiple, it's the smallest number, which is both a multiple of 9 and 4 as well. And the smallest one is 36. So now we have a couple stratagems, that's not correct proper use of that word. We have a couple strategies here we can now use. We can jump on and hit the gas right now, and we can multiply both sides of this equation by that least common multiple, that least common denominator. In fact, that's actually probably going to be the best idea here. Dealer's choice. So we know the LCD, the least common denominator, is 36. So I'm going to multiply both sides by it. And when I say multiply both sides, I don't just mean the first thing on both sides. I mean you got to do the entire thing. Every gosh darn thing gets multiplied by a 36. Because I can do that. I can multiply both sides of an equation by any number I want. If I choose, it's usually not smart to just say, let's multiply both sides by -21. There's no reason to usually do that, but if you have picked a smart value, which we have, then it is helpful to actually do that. That means that 36 gets multiplied to y over 9. That means that 36 gets multiplied to 1/4. That means that 36 gets multiplied to y over 4. That means that this 36 gets multiplied to 1/4. Now, Josh, why did you do that? Why are we multiplying both sides by 36? Because I know what I'm doing, and I know that that's going to cause all denominators to cancel out completely, and fractions, we will send them back to the 7th circle of hell where they belong. Fractions have no place in this world. They are evil, and we will destroy evil with our arsenal of freedom. So we're multiplying by 36. I just put it over 1 so you can see how fractions are working. So now I'm going to simplify using cross multiplication. I'm going to look at the y and the 1, and they don't simplify. We're not going to worry about that. But the 36 and the 9 will. That'll become a 1 down here and a 4 up here. Because 36 divided by 9 is 4. Over here, I'm going to cross multiply. The 1s won't do anything with each other, but the 36, that's going to become 1 and 9. Over here, same business. Over here, similar business. So now I've got a bunch of fractions, but now all these fractions just have one denominator. So when I multiply the fractions, maron, it's going to be easy. This first one is going to be 4 times y, aka 4y on top. On bottom, you're going to get just 1, because now you just need to do 1 times 1. But wait a minute, putting a fraction over 1 is unnecessary. It doesn't do me any good. So I'm just going to call it 4y. That was the whole reason I did that. I picked 36 because it's going to completely get rid of fractions. That's the beauty of it. Over here, I'm going to get 9 times 1, and it's plus, just because there was a plus sign here. 9 times 1, which is just 9. And then on bottom, it's technically 1 times 1 again, but for the same reason, I ain't got to write it. I tell you what, that makes me happy. That warms up my heart. All right. Over here, you're going to get 9 times y, or just 9y. On bottom, you just get 1, so I don't even need to write it. And then finally, I'd get 9 times 1 again. And bada bing, bada boom. Oh, look at that. Look at that beauty down there. Yes, that is so beautiful. There's no fractions. Oh, thank the maker, there are no fractions. I feel like doing a little dance right now, but I won't. So all that, it's not gone, it's just I ran out of space. So now we just need to solve this part. We just need to solve what's left over. Someone asked me a question. So now, Xavier, you see how to solve that? We would just move this 9 over, move this 9y over. I'll do it real quick. I'll do it a little bit quicker. But now with fractions going, I mean, it's much, much simpler to deal with. Now I'll subtract this 9y over to get all the y's on the left-hand side. But yeah, it's so much better to work with now. You're going to get negative 5y equals negative 18. So your final answer will still be a fraction, but that's no biggie. That's no big deal. I'll divide both sides by negative 5. I'm doing a negative divided by a negative, so y just becomes the fraction 18 over 5. So the final answer is a fraction, but you can't help that sometimes. And that is the answer. You don't sweep away that fraction because it is what it is. So Xavier seemed pretty happy with that explanation. Thank you, Xavier. Do you have one for me? Okay. Which homework is it? That's that converting between decimals and percents homework. Which number? Number 1, okay. The percent formula? Mm-hmm. What is 9% of 900? That's what it wants to know. Good question. So it wants us to use the percent formula. So sometimes this is read as A is P, hold on, percent of B. And what the kind of the way that they make you remember it, the word is makes us think of equality, the equal sign. The word of makes us think multiplication. So you have 3 possibilities here. You have A, P, not Adrian Peterson, and B. A is usually thought of as the part of the number, but that can be a little bit misleading. You'll see why. Not always, but P is the percent that you're talking about. But when you're actually sitting down and doing the math, you need to write it as in decimal form, which is awfully confusing. I'll give you that. How come you don't just leave it as a percent in there? Well, that's just because it's not how the actual math works behind the scenes. Then B is kind of the whole, or it's everything. So in this case, what's usually going to happen is you have the 2 things that you know, and then you're looking for the unknown, the third thing in this equation. So let me make the equation a little bit better looking. So in reality, for what we actually have, A is going to be the part of the whole that we're looking for, and that's what we don't know. So I'm going to put a question mark there. And the question mark means that's actually what we're going to be solving for. P is going to be the percent. Now it's 9%, but remember, close, 0.09. Because remember, we have to write it as a decimal. And yeah, you're saying like 9.0%, 9%. You would move it 2 places to the left to get it into decimal form. And then finally, B, aggressive. B is going to be that whole, the entirety of the 900. And so the thing we don't know, the question mark, we're going to be solving for that, and we're just going to leave it as its variable. A equals, now we can actually substitute the values we do know. 0.09 times the number 900. And now this is where you say, I'll just go grab my calculator and go toss all the numbers in there and it will give me the answer and we will go run up and down the streets and cheer for ourselves. What's wrong with that? Can you do that on the exam? Can you use a calculator on the exam? No, get out of here. You can't use the calculator. Oh, okay. Uh-oh, SpaghettiOs. That's okay. Here's what we're going to do. We're going to proceed. We're going to have to do it via old school multiplication because it's multiplying a whole number with a decimal number. We will put the 900 first. Let's use a different color. What color would you like? Green it is. We'll put the 900 first. It looks like Christmas. And Christmas is the second best holiday. And ladies and gentlemen, what's the first best holiday? Halloween. Halloween. Actually, Thanksgiving is up there for me as well. So we're taking 900 times 0.09. Remember, once you know how many decimal points have to be there in the final answer. There's going to end up being 2 total decimal points because there's 2 here. There's none up here. There's 2 decimal points here. So we start with the 9. 9 times 0 is? Very good. 9 times this 0 is? Very good. 9 times 9 is 81. Now, we still have 2 more zeros down here. So remember, you got to give yourself a 0 on the next row. But then it's just 0 across the way here. It's 0 times 0, 0 times 0, 0 times 9. So this just gets filled out with a row of zeros. The next line, you have to give yourself 2 zeros to start with. Then you got to take this 0, do 0 times 0, 0 times 0 again, 0 times 9. It's very boring. Just like my science fiction novel that I'm writing. And now we do our addition. We get 0 on the right, then 0 again. 1 plus 0 plus 0. 8 plus 0 plus 0. This 0 on the left there is just not even worth writing. So is the final answer 8,100? No, because this had no decimal points, but this had 2 decimal points it went out to. So the final answer needs to at least initially have 2 decimal points. Ooh. 81.00 or just by itself, 81. So what is 9% of 900? 81, that's correct. All right, out there in the Zoomosphere, I'll give you guys an opportunity to give me another homework assignment you'd like, or if you're comfortable, you like what you've seen so far. I thought there was a machete under the desk here. It was just an umbrella. You got time for about one more. Okay. I have a question 11 on 6.2 linear equations with one variable. So yeah, let me go pull that up. So section 6.2 homework, number 11. And Xavier, why don't you give me the numbers you have? Because I'm going to see slightly different numbers technically. And I want to work the exact problem you're giving me. Ooh, this one's interesting. Okay, never mind. You can't exactly give me the numbers you're seeing per se. This one asks a weird question. It says, determine whether the following statement is true. If the statement's false, make the necessary changes to get the right answer. So, determine if the equation x plus 1/2 equals 1/3 determine if that equation is equivalent to the equation x plus 3 equals 2. Xavier, what kind of numbers are you seeing in your problem? And I'll alter it just enough, or alter it to be your problem. Is this the right one? Okay, cool. X minus 1/3 equals 1/2. So let's just alter it just a little bit. And then is this other equation, x plus 3 equals 2, is it the same equation you're seeing? X minus 2 equals 3. Okay, so then let me just alter it. Okay, so this is the problem set before us. Determine if the equation x minus 1/3 equals 1/2 is equivalent to the equation x minus 2 equals 3. Here's the logic we're going to throw in behind it, the definition of equivalent. Two equations are said to be equivalent if they have the exact same solution set. In other words, if all values of the variable that solve the equation are the same in both cases. So for instance, these two equations are equivalent. 3x minus 7 equals, how about, let's make it interesting, equals 17 is equivalent to the equation because, see, look, if I were to solve this, you'd get x equals 8. It's equivalent to the equation negative 16 equals negative 2x. They look completely different, don't they? Like they look wildly different from each other. But if I were to solve this first equation, I'd add 7 over, get 3x equals 24, divide both sides by 3, get x equals 8. So this first equation has a solution of 8 for x. This one, all I got to do is divide by negative 2 on both sides, and either way, I'd get x equals 8. So because, even though they look wildly different, but because they have the same solution set of 8, these are actually two equivalent equations. So now, really what you have to do, there's a couple things you can do here to solve this. My way is to just solve both of these equations. Solve each of them, and if you get different values of x, you know they weren't equivalent. It doesn't matter that 2's and 3's are flowing around in both cases. They got to have the same solution set. So I'll solve this one first. I'd need to get x by itself. I need to add 1/3 to both sides. I'd get 1/2 plus 1/3. I need to get common denominators, so that's going to become 3 over 6 plus 2 over 6, which ultimately becomes 5/6. Oh, oh, gotta do my mob guy voice. So the solution to the first equation there is 5/6. And then you can clearly see the solution to the second equation here, not gonna work. You're gonna get just 5. 5/6 is not the same as 5. So no, they are not equivalent. Now the problem goes one extra step and says, how can you remedy this situation? Just what you need to do is go look at the different multiple choice answers and find 2 of them that are equivalent equations. Each multiple choice answer will say, oh, these 2 are, it'll give you 2 equations, and you need to determine if they are the same, if they have the same solutions. Does that help out, Xavier? Cool, cool, cool. So yeah, equivalent means at the end of the day, all that's happened is because they have the same solution for x, all they did was do some manipulation that's allowed to both sides of the equation. They just added a 5 to both sides, or subtracted or something, divided something, or multiplied by something. So, for example, let's say you had x equals 5. That is an equation because there's an equal sign, and it's already a solved equation. It's already got x by itself. It looks exactly like we want. Let's say you took that same thing. These are obviously equivalent because they're the exact same thing. That should be obvious. They're both the exact same equation. But let's say I was bored one day and I decided to add 2 to both sides over here. So now I got x plus 2 equals 7. And hey, let's go wild. Let's say I also decide I want to multiply both sides of the equation by 3. So that 3 hits everything on both sides of the equation. So now I've got 3x plus 6 equals 7 times 3 is 21. Why? Well, I just picked some arbitrary numbers. Everything I've done, I've added 2 to both sides, I've multiplied both sides by 3. Those are allowable operations according to some of our rules for equality. What if I did something else over on this other equation over here? Remember, x equals 5 originally was equivalent to x equals 5. What if this time around I decide I want to start by multiplying both sides by, how about -4? So I'm going to multiply both sides by -4. I don't know why I put it down there. Come on. Okay, so now I've gotten -4x equals -20. And then let's say I decide I want to subtract 9 from both sides, whatever. So I'm going to get -4x minus 9 equals -20 minus 9 is -29. Okay, I don't know why you'd want to do that, but if you're bored one day, you could. Now these 2 equations now look completely different. They look wildly different from one another. But they're still equivalent because everything I did to each separate case was something that's allowed under the rules of addition, subtraction, multiplication, division, and balancing it on both sides of the equation. So this thing over here is still equivalent to this thing over here. Because at the end of the day, they were both just x equals 5. They were both had the same solution of x equals 5 no matter what I do. So that's kind of what it's testing you on there. Okay, so that's about it for today. Remember, your next exam is a week from today, and an announcement will be being posted here in about 30 minutes on Canvas with all the information you need. I just copy and pasted the previous announcement and changed the information for this upcoming exam, so it's really straightforward. You guys have a wonderful weekend. we'll see you guys in Zoom on Tuesday. On this Tuesday, September 22nd, we'll be doing only virtual. And we'll see you guys there. Bye.